We're going to make a video about this little wonder. This is a LED street light. It's a broken LED street light. Here's the aluminum cover. That goes right over this area. And it's broken. So it's not any more use. And I managed to get it because it's broken. And hey, just thought I'd play with it. A couple neat things. One, LED street light is going to put out a pretty intense light. You might find it useful at some point for something. Well, I think it's maybe even neater is each one of these light bars. There's 6 light bars in this thing, and each one of them can be taken out separately. Apparently, they each are wired separately. We might find a good use for those individual light bars, as well as maybe making use of it in its entirety. So, just thought I'd share with you how to convert this street light into something useful at the house. Whether you use them as individual light bars or as a whole, it might change the electrical design slightly, but the design we're going to use would work no matter whether you used one or all 6. I just sized it so it'll fit all 6, which means it'll readily fit any one light bar as well. So let's go play, see what we can come up with, see what we can learn about this LED light. Well, let's start off and talk about what we found when we opened up the light. There was a bunch of electronics in it, which, if you saw the light just now in that metal cover area, there's no electronics but a few wires coming out of the lights. This is the main thing I guess we found. There was a number of other circuit protection devices and I think surge stabilizers, things like that. But there were 2 of these in there. It was actually controlled in 2 banks, 3 and 3, 3 light bars in each bank. So there's 2 of these wonders. And if you notice, I'm not sure, hopefully you can read this. It says right down here that this is an LED electronic driver. Don't confuse this with a fluorescent ballast. It has a similar appearance and structure to a ballast, but this is far from a ballast. But this is basically a transformer and rectifier, which is converting AC voltage into DC voltage of a certain range. So let's look. I'm not sure if you'll be able to make this out on the video, but basically the voltage in is 347 to 480 volts AC. And it is a single phase. It's not 3-phase like typical 480. You're just taking one leg of the 480. The frequency 50 to 60 hertz. The input's 0.5 to 0.35 amps, depending upon which voltage input you're using for this thing. And it says right there too, 347 volts to 480 volts. So we don't have 347 to 480 in our house, and so right off the bat I just started stripping out these electronics, knowing we were going to have to go with a different circuitry. And so let's talk about what the output of this device is. That's what we want to try to match. And it says right here, the amperage out, I out, is 0.7 amps DC. The voltage out is 60 to 210 volts DC. And then the max volts out is 250 volts DC. And the max amperage is 0.76 amps DC. So basically we need to take, if we want to do this on house current, we need to take our house current, which here in the US is 60 hertz, 110 to 120 volts for single phase, and we want to take that and convert it to something that this thing can use, which 120 volts DC or around there, more than that even's fine. And the amperage load per bank is about 0.7, so that's a 1.4 amp overall draw. So we did some calculations, we started designing a circuit, and I'll show you that that design and a little background on developing that circuit. Well, I'm going to hope the glare and whatnot's not too bad here, but let's talk about this LED light circuit that we're developing. We're going to have an input voltage of 120 volts AC. Now, when we talk about input voltage in AC, we measure it with our meter. That's an RMS voltage, which means root mean square. It's basically the average voltage over the positive cycle of AC, and which means that your actual peak voltage, even though we call it 120 volts, actual peak voltage is closer to 170 volts AC. And you determine that by multiplying your measured RMS voltage by the square root of 2, which is 1.4 something. So that's the actual peak voltage. You'll see in a minute why it matters. The frequency in the US here, 60 hertz. And so then, if we decide to use a bridge rectifier, I'm not going to bother you with the bridge rectifier. You can find it online. It's basically 4 diodes. A full bridge rectifier is 4 diodes in a circuit where the diodes shunt the negative voltage, and basically you end up taking the absolute value of the voltage in an AC cycle, and I'll show you that on a graph here in a minute. But and then so you take this voltage input, you go into a rectifier, this 4 diode circuit, and that circuit has a draw. I estimated this one to be 1.1 volts DC. Turns out it's greater than that, but it's not a train wreck. It's not a lot. So that means that our outcoming volts would be 118 volts DC on an RMS basis. Turns out ours is 115 or so in this case. But to get to that, you take the input voltage, which is this one, the RMS voltage, and you subtract 2 times the delta voltage, the change in the voltage drop across the diode, and so we get about 118 volts DC. And then the frequency changes when you go through that rectifier. It doubles over what this initial input voltage was. So if you're on 50 hertz, for example, you'd get 100 hertz here. At 60 hertz, we get 120. It's basically the incoming frequency times 2. So let's talk about that part. Here is a sine wave that represents 120 volts AC. What you'll notice is that the peak voltage here is at 170-ish volts, but when we talk about RMS, we're talking about the RMS voltage being down here at 120. If you want to go study up on the root mean square technique, it's available. You're welcome to. But basically, this becomes something of a mean, the 120 volts that we measure. And so just important when you're doing rectification to understand, or when you're doing an AC to DC converter, which is more than a rectifier in this case, but it's important to understand that your voltage is going to be more related to your peak voltage than to your average 120 volt voltage. Okay, so when you go through that rectifier, what happens is it takes the absolute value of the sine wave. So basically all negative values become positive, all positive values remain the same, with the exception that you do get some voltage drop across the full bridge rectifier. So you're basically going to generate a graph that looks like this guy. So you have your 0 to 170. Again, you need to subtract your voltage drop across your rectifier, and I did in this case. It's just an example. And it comes back down to 0, and then it peaks back up again. So basically it's inverted. It's inverted this curve and brought it up on top. So your total magnitude of your positive curve does not change, with the exception of the voltage drop. It just inverts this negative portion of the sine wave that AC voltage is based on. So that's what you end up with. Now when you do this, you now have good positive flow. So why does it matter? Will the LED not work on AC? The answer is yeah, it'll work. The LED works. I tested it quickly. We didn't want to run it that way for any length of time, but it's only going to function right here. So out of this time segment, and this is time based, out of this time segment, it only is going to function here out of this entire period. So until it comes back up again, will it function? And what that creates is, in this case, dim light, and to some extent an unstable light. It's kind of hard to see 60 flashes per second, but it is slightly noticeable. But more than anything, you just have very low light output, because you're only driving the LEDs in this condition. And functionally, it means you're turning the LEDs off 60 times a second. I don't think that's going to be good for an LED. I'm not an electrical engineer, but I'm betting it's not a great thing. So one of the reasons that when I did check it, I did it very quickly because I didn't want to sit there and turn it off and on thousands of times by leaving it plugged in for an extended period of time to AC current. So that once you put the rectifier in place, you end up with this still alternating current, but it's not negatively alternating. It doesn't go below zero. It goes to zero, though this graph represents it being a little above zero. It goes to zero, but it doesn't go negative. So while it's, I guess, somewhat turning it off down at these 0 points, it's certainly not cycling negative. But again, I don't believe this is going to be a positive for the light circuit. And it's certainly, again, you're only going to get light output part of the time when your peaks are adequately positive to drive the LEDs. Now they might be adequately positive at 60 to drive the LED, but it's not going to drive at the same intensity as it drives at 170, and then it's going to come back off again. So overall, your average light output is going to suffer from having a circuit that looks like this. So what do? Well, now that you have, let me go back. Now that you have this circuit, what you need to do is take that ripple out. And you take that ripple out by capacitance. Basically what you want to do is you want to store energy on the high part of the curve. And then you want to discharge energy from your capacitors as it steps through these portions of the curve. And then you want to begin to store energy again and come back down again and use that stored energy to maintain an average energy level feeding the LED that's much higher than this curve would represent you're doing. So how do you do that? Well, you add capacitors, you add capacity to the circuit for the storage of electricity. So that's the next step. We've got a 118-ish volts, and it's more like 115 in our particular case, because this estimate for this delta, the voltage drop is a little whack. So we need to determine a capacitor. I happen to have some 1,000 microfarad 300 volt capacitors. Here's an example of them. And so if I could use these 1,000 microfarad, that would be very useful. So what I did was I did some calculations basically to see how many of them I needed. I assumed that my amperage for my final amperage needs to be about 1.4 amps. I think that may be slightly overstated. That's fine. The duty cycle, excuse me, basically the duty cycle is how much is charging and how much is discharging. In this case, the 70% is how much it's discharging. So that duty cycle is an important number. When you use this number for calculations, it's 0.7, not 70. And then your peak-to-peak ripple, basically how stable do you want this voltage? If you can take this, we'll call this a ripple, out, how little ripple is enough ripple? In our case, what we've said in this calculation was that we would take 4 volts. 4 volts is adequate in ripple. So as long as it doesn't vary more than 4 volts, we'd be happy with that, which is about 2% ripple. If you take the voltage ripple that you're allowing, your actual voltage that's being applied times 100 divided by the actual voltage that you're going to have times 100. So what is the actual voltage? Well, the actual voltage, because we're going DC now, is no longer going to be based on the wave. It's going to be flat or very near flat. And so the actual voltage is going to be the RMS voltage, which is this number up here, 118 volts calculated, a little off because of the voltage drop error. But we said it's going to be about, you multiply that times square root of 2, and that gives you about 167 volts. And so we're saying 4 volts, no more than 4 volts below that 167, which is about 2% ripple. So if we do a calculation to determine what capacitance we require, This capacitance is in microfarads. The actual formula here is typically in farads. So if we convert from farads to microfarads by multiplying by 1,000,000. So you take the voltage, final voltage, which we estimate to be about 1.4 amps, only based on this LED driver telling us that it was capable up to about 0.7. And we had 2 of them, so we assumed it's about 1.4 amps. Probably a little overstated as it turns out. That's fine. Times your duty cycle, 0.7, times 1,000,000. Convert the calculation from farad to microfarad. And then your ripple voltage, how much voltage you're going to allow, you divide by your ripple voltage. So dividing by 4 volts. And then we divide by the frequency after the rectifier, which we said is 120 hertz. You do all the math, and it comes out and it says you need about 2,000 microfarad of capacitance available in the circuit. So in our case, as I stated, we have 1,000 microfarad capacitors readily available to us. That's this number here. And if you run capacitors in parallel, they become additive. So if I run 2,000 microfarad capacitors, I'll end up with 2,000 microfarad of capacitance within the circuit. So that's what we decided to do, and that is what we did. And then we actually measured voltage. First, this 120 volt AC number that we used to calculate turned out to be 122.5 volts AC at my particular house. Depends on where you're at. Every house is going to vary, and most likely going to vary over the term of a day, or you're guaranteed 110 to 120. In this case, we're a little over 120. So if we look at the final circuit, where we have a full bridge rectifier in combination with 2,000 microfarads of capacitance with no load, in other words, the light not hooked up, but the circuit plugged in, the light not hooked up, we had 165 volts DC measured. So if we go back up here, 167 volts is what we estimated it should be, and that just goes back and tells us that this delta V across the diodes in the full bridge rectifier is underestimated slightly. So no problem. We have 165 volts DC without load. And then we put the load to it. When we actually hook it up to the light circuit, we drop to 162 volts DC, which is very close to our full 4 volts that we set to calculate our 2,000 microfarad capacitance requirement. So we've got 2,000 microfarad, and we have a little less voltage drop than we expect, which goes back, if you look at the formula, it probably indicates that the actual amperage requirement is slightly less for those circuits, because certainly this LED driver we looked at a while ago doesn't tell you how much amperage, it just tells how much it's able to produce, not how much is necessarily going to be consumed by the circuit. So don't let that fool you. So we ended up with 162 volts DC with a relatively low ripple of slightly less than 2%, and I'm tickled. So let's go see what it looks like when we hook it up to the light, and get your sunglasses out, you may need them. Alright, so as we get ready to plug this in, I just want to make a comment. Right now you'll see that over here I've got this hooked up with some test leads. Be very careful. That's a lot of capacitance. 2,000 microfarads holds a lot of energy. You plug this in, you charge it up, and then if you unplug it, and I'll show you what happens when you unplug it, it will bleed some of that voltage down, but there's still the potential for stored voltage in those capacitors, not even potential, reality. And so if you go and toy with that too much, when it's got that stored energy in those capacitors, it could bite you. So just be aware. You can discharge those capacitors by simply jumping across the wire. Once it's unplugged, you can jump 2 wires and it'll discharge, or you can leave it plugged in for enough length of time potentially that it will ultimately discharge through the circuitry and the LEDs. But understand, it may actually bottom out and not remove any more stored electricity, and you could still have some stored in there. So be careful. Capacitors can bite you. Let's plug this thing in. go. So, blinding, it's quite bright. I did try to take some pictures. No, that's not true. I did take pictures. I took pictures of it in 3 different modes, with 120 volts AC, with the 120 volts DC, once rectified but not stabilized, still had ripple from 0 to 160 some volts, and then took a picture of it in the mode you see right now, which is once it has stabilized at roughly 2% ripple and 165 volts, and the difference is dramatic. Regretfully though, when I took the pictures, I didn't think about the fact the camera was just going to adjust for the peak light. So basically every one of them looks very much the same, because the camera adjusts its shutter speed to accommodate. So bottom line, this thing produces a ton of light. Whether I use this as a single unit, whether I use this thing as a series of light bars, I think it'd be very interesting actually. Used to raise coral in saltwater aquarium. Lighting's critical for coral. I'm not sure about the frequency of this light, whether it's how well it represents sunlight, but if it represented it well, these would make some pretty neat light modules individually built into a light bar for a coral or other type fish tank. But I don't know what we're going to do with it yet. We're just going to play with it, and we did, and we love it. It's fun. You get your hands on a street light, you might find it useful. Be sure and check your circuitry. Make sure that you understand what your requirements are. In my case, with that LED light driver and that I was able to take out of there and able to get right to the actual wires going to the bars, light bars, I was very much able to understand what voltage, what amperage would work the best. This could be turned up. I think that thing said max 250 volts DC output on the electronic driver. So I assume these things could handle that level of DC voltage. In our case, we're only at 165. But hey, it's ridiculously bright enough without having to go to that extreme. So remember that 165 volt DC rectified from 120 volt AC could potentially drive LEDs for you. Double check all your LEDs, make sure that they don't already have drivers built in. A lot of like the LED fluorescent tube replacements, they have built-in drivers that convert to power. They basically have rectifiers built into them. And so, yeah, it's not a given that this voltage, this amperage, this DC versus AC is what you need. In this case, by doing some research on the light, we were able to determine that this was correct. Nifty, fun, maybe boring to you, but I entertain myself with such silliness as this. Y'all take care. Have a good day. Later.